I'm really pleased to give this lecture here in the City of London because I am a Londoner. Hey. I may now be living in the city of Bath, which is a wonderful place to live, but I was born in Finchley, and Margaret Thatcher was my MP, and I then lived in Harrow for a long time, and more recently lived in Kilburn. So I am definitely a Londoner, born and bred in London, and quite a lot of what I'm going to talk about today is about the City of London. And I hope at the end of this lecture you'll be able to go out and actually find some maths in the city that's all around us. But cities have been around for a very long time, much earlier than London. There's a lot of controversy about which is the oldest city in the world. Here's one of the contenders, the city of Uruk in the Middle East, which is at least 6,000 years old, possibly earlier. There are cities in China that are probably older than that. So human beings have been living in cities for a very long time. And now, half of the world's population, in fact, over half of the world's population, lives in a city. And this picture is not completely clear, but this is a map of the world. Here we have the UK with the cities of London and Birmingham, but we are minnows compared with Tokyo over here, Delhi over here, and Mexico City over here, and Shanghai over here. These are mega cities. If you count up all of the bits of Tokyo, because Tokyo is several cities that have kind of glued themselves together, there are 38 million people living in Greater Tokyo. I've been to Tokyo. Yes, there are 38 million people there. It's very, very busy, but it's got a great transport system so you can get around. So over half of the world's population lives in a city. This is going to rise. It is expected by the year 2050 that over 70% of the world's population will be living in a city. And just for comparison, here are the primary urban areas of the UK. Here's London. This is the Bristol Bath area where I live. And interestingly, the largest urban area is sort of Leeds, Huddersfield, merging over into Manchester and Liverpool over here. So these are the primary urban areas of the UK. So, what is a city? Well, a city is really three things. The primary thing about a city is the people and the houses that they live in. But that city of Uruk and all the early cities were not just gatherings of people. What made them into a city was the infrastructure that grew up to service it. Someone once said a city is a large group of people plus an efficient sewage network. Okay. And if you think about it, cities without sewage had a lot of problems with disease. So here are the infrastructure, sewage, defence. The early cities were defined by the walls around them. And if you have time after this lecture, wander around the museum and you can see some of the walls of London actually out of the walls, out of the windows in this museum. You have to have a transport system, retail, communications, education, energy. Culture is very important in a city. And of course, most cities, very much including London, are based around business. But the third most important part of a city, and we'll touch on this quite a bit, is government. So without a system of government, and that includes policing, none of this would operate. It would just be anarchy. So these are the three things that make up a city. And we're going to kind of touch on all of these in this lecture. But cities are complex. Many things go on in a city, and things go on at different scales. I am a Londoner. Sadly, my two children are not. Both were born in Bristol, but my daughter now lives in the fine city of Glasgow, and Glasgow has in it an Institute for Future Cities at the University of Strathclyde. Quite a lot of what I'm going to talk about today is based on some of their research. And here is a map that they have produced of Glasgow, not showing the streets, but it shows it at different scales, showing activity. So this is where the population is, showing the density of the population. The darker it is, the denser it is. Then we've got house prices underneath. So house prices are concentrated over there. Deprivation over here. These are areas of high deprivation, and these coincide with drug misuse here. So many things happen in a city at different scales, and trying to understand how things happen at different scales and how they interact makes up what we call a complex system, and it's something mathematicians like myself are really interested in studying. So, let me get this work. There we are. Cities are now very interesting areas for mathematicians such as myself to model. And there are various names associated with this modelling. So you can read papers on things called city analytics or on future cities. But what I like most, and we will certainly touch on this, is the term the living laboratory. So we can come up with theories for how a city will operate. We can actually see those theories acting now on the population. And the reason we can do this is with the rise of social media. We have enormous data now on how people are interacting, both with each other and with services. And this not only allows us to look and see how good our models are of how cities grow and develop, but very importantly, this allows us to plan into the future to see what future cities are going to be like and how we can make them better places to live. So that's something I really want to touch on today, how mathematics can help us understand a city and also allow us to plan for the future so that London can become an even better city than it is now. And of course, I firmly believe it's the best city in the world. So here's my talk. Firstly, we're going to look at how cities grow and expand, how you start from something small and how it gets bigger. Then we're going to look at how cities break into communities, because in many ways it's the communities that make up the character of a city. Then we're going to have a look at how we travel around, because that's increasingly important and can make or break a city. And then sadly, cities attract crime, so we're going to have a look at the mathematical way that we can understand how crime occurs and how it can be dealt with. And then given that many of us spend most of our time going to cities to go shopping, I thought I'd talk about retail. And then last and certainly not least, I want to give you a quick mathematical tour of the wonderful city of London. So that's the agenda for today. So let's have a look now about how cities grow. So most cities, well, no city started large. All cities started small and grew from that. Well, at least that's historic cities. I suppose some modern cities like Milton Keynes might have started a different way. But most cities start small and grow. To give you an idea of how things are happening in London, it's kind of interesting. Here's London, and the blue shows how people are moving into London. So there is a big influx of people into London from the northwest in particular, and from a bit from the west as well. And the red shows that where people go to from London, so probably when people retire, they then go off here and live on the south coast. So we have an afflux of people out of here. So this is everybody. But if you have a look at people aged in their 20s, sort of new professionals, there's a huge influx into London from all over the country. It acts as a pulling power for all of the UK, everyone going into London. So cities grow by people having children, by people coming in through immigration, and by coalescence. So the question is, as people arrive, how do cities change? And in particular, how do the services and infrastructure in a city change to accommodate the influx of people that are coming in to make them up? Do cities grow in one way or another? So this is a question we can ask mathematically, and it allows town planners to plan into the future to see how services need to grow into the future. So I thought I'd start this discussion with asking a question, which is quite a famous question. It's supposed to be an interview question. It's called a Fermi question, but I still think it's really good and very much illustrates the ideas I want to talk about. And it's this: how many piano tuners are there in London? Is there a piano tuner in the house? I'm not sure. So this is a question you might think has nothing to do with mathematics, but is actually a question that you can answer mathematically by applying logical reasoning and the sort of reasoning that we need to apply in order to understand how cities grow and services develop. I admit piano tuning isn't the most vital of services, but still it's an important service if you happen to own a piano. So I shall take you through the calculation to see how we can estimate it, and then we'll unpick that to see how we can generalize that to other things. So here is how it works. Let's assume we're in a city. We have capital N for number of inhabitants. A certain proportion of those will own a piano. And you can kind of ask around and ask your friends, do you own a piano, do you not? And you can come up with a figure for what proportion of that number owns a piano. And it turns out, by vast amounts of checking around and asking all my friends, it's about 1 in 50. Of course, it depends slightly on what friends you have, but roughly 1 in 50 of the proportion of a city's, 1 in 50 of the number of a city's population will own a piano. And a modern piano is pretty good most of the time, but over about a year, it goes out of tune. So that means that if you take N is the number of people in the city, N over 50 is the number of pianos that need to be tuned in 1 year. Now, piano tuners are normal human beings. They don't work every day of the week. They don't work every week of the year. So the average working year for a piano tuner is about the same as the average working year for any other person, which is about 230 days. So if you take N over 50 and divide by 230, that's how many pianos need to be tuned per day per piano tuner. But again, if you ask around and look around, a typical piano tuner can tune about 5 pianos a day. So if you divide that by 5, you get a number Z, and that number Z gives us an estimate for how many piano tuners you need in London. And if you work it out for London, Greater London, population Greater London is about 10 million, you find we need 174 piano tuners. I tried to double check this, but I couldn't find accurate information, but it seems about right. When you apply this to Bath, you get 2, and that seems exactly right from the estimates I found from Bath. So this is about right. So this gives you, it's a slightly trivial calculation, but it gives you a way that a town planner might mathematically tackle the problem of how you need certain types of service in a city by making these sort of estimates. But I've slightly cheated here. I've made one very big assumption, and it's a reasonable assumption. And the assumption is that the number of pianos in a city, and therefore the number of piano tuners, grows linearly with the city. And what that means is, if the city doubles in size, so the number of pianos doubles in size, and therefore the number of piano tuners doubles in size. So this is called linear growth. And linear growth looks like this. It's a graph where it's a straight line. If you double the size of the city, you double what you need. And many aspects of a city grow linearly. This is something you can test very easily by just taking a population census. The number of teachers in a city grows linearly because essentially the number of children in a city grows linearly. The number of houses, or to be more precise, living spaces, grows linearly because families are roughly the same size. Number of pets, and therefore the number of vets, grows linearly. Number of schools, and it turns out the number of health workers, and this is interesting, I'll come back to why that's interesting in a minute, all grow linearly. So this is very straightforward for a town planner. City doubles in size, you double the amount of schools, you double the amount of health workers. If everything was linear, things would be straightforward, but there are different types of growth which are not linear, so that when you double things, they don't double. And one of these is what we call sublinear growth. And one of the features of a city is that they show economies of scale. So an example of this is hospitals. So in the city of Bristol, where I used to live until quite recently, the number of hospitals has actually been going down. And the reason it goes down as the city gets bigger is that the small hospitals combine together to become big, very efficient, large hospitals. So the actual number of hospitals goes down, even though the city is getting bigger. You get economies of scale. So this is sublinear growth. Airports are a bit like this as well. Typically what happens with an airport is a city doesn't have an airport until it gets to a critical size, and then you get an airport. And then it will stay at one airport for a very long time until you need another one. So you get this sort of growth here. We call this thresholding growth, and these are all sublinear. This is where a city is showing economies of scale. So this is this big hospital in Bristol, which is showing this economy of scale. You get various other economies of scales. Train stations don't grow linearly with cities in terms of numbers. And funnily enough, the total length of the roads in a city doesn't grow linearly. It actually grows significantly sublinearly. So these are cases where the amount of infrastructure, in fact, grows slower than the city and is therefore relatively easy to accommodate. And one of the things you have to do with modelling is try to identify which of these applies. But there's another type of growth which is rather more concerning or more interesting for a town planner, and that's what we call superlinear growth. And that's where the growth of what you need to provide grows faster than the city is growing. So if the city doubles in size, you might need 4 times as much rather than 2 times as much of this thing. And a very good example of this is social interactions. So if you have n people in a room, how many possible conversations can you have? Well, each person can talk to every other person apart from themselves, and presumably that person is talking to the other person. If you talk to someone, they generally talk back. So the number of conversations that you have is n times n minus 1 divided by 2, and that grows like n squared. So the number of conversations that you have in a room quadruples if the size of the room doubles. And in a city, that means the number of social interactions that you get quadruples rather than doubles if the city doubles in size. And that means the number of short journeys people want to make to meet each other is going to increase, and the number of telephone conversations, in other words, the amount of traffic the mobile phone company has to deal with, are all going to go like n squared. They're going to quadruple rather than double as the city doubles. So this puts quite a significant strain on the resource, and again, something that we need to be aware of as cities grow. What goes like this? Well, the number of, say the number of short journeys is going to grow, the amount of communication is going to grow. And what's interesting, and I think it's to do with the fact that you can have more networking opportunities and better communication, and this is well testified, is the number of professionals, in other words, young people in business, grows much faster than the city grows. Okay. So this is either a good thing or a bad thing, whichever way you want to look at it, but it's something, an aspect of how cities behave. So that's one of the kind of basic things that we need to think about when we model a city using mathematics. So cities, as I say, are really made up of the people in them. I mean, the sewage is all very well, but if it wasn't for the people, there wouldn't be a city. So cities cities are made up of people, and what I want to talk about now is the way people network and form communities, because that's really how the character of a city is formed. The nature of the interactions and the friendships that people have in a city essentially define its character. And this is something which mathematics is actually very helpful at understanding and also allowing us to predict how cities then go on to form communities. So how do we study all this? Well, the way we study this is through what we call networks. We're going to meet this again when we look at transport. So this is what you're looking at here is a social network. A social network is a group of people, here they are, who I shall call nodes, and in a city you would have n of these, who are interacting with each other in different ways, and you have a number of edges, which are friendship links, so you draw an edge to someone if they have a friendship. And we'll assume that if I'm friends with you, you're friends with me, so that edge goes both ways. So this forms what we call a social network. And networks are key to helping us understand how friendships or social interactions can develop, and they are very widely used by companies like Facebook or mobile phone companies to help predict the behavior of people in large communities. So as I said earlier, the number of edges that we get, that's the number of friendships you might have or conversations, is n minus 1 over 2. It grows like n squared, so it goes up by a factor of 4 if the city doubles in size. That's a simple network. Let me show you what a city really looks like from a network point of view. It's more something like that. Okay. Pretty difficult. I mean, let me again indicate how big this is. There are 10 million people in London, about. That means that there are 10 million squared. That's 100 trillion possible links. And that's quite hard to represent. And that's why this looks kind of a mess. And that's why mathematically we need to be quite sophisticated in how we analyze this and decide what's going on. So I'll tell you one thing which is kind of neat, just to sort of show you one sort of way that mathematicians can understand this and help understand our social lives, as it were. So here we have a friendship network. Are we going to let me do that? There we are. There's our friendship network with people making friends. That's what it really looks like. But if we think about it, in a network, who are you most likely to make friends with? You're most likely to make friends with people who already have a lot of friends. If popular people have lots of friends, and you're much more likely to be friends with someone who's popular than not because they've got lots of friends. Okay. People who have lots of friends are more likely to be friends with you than people who are not. And what this means is that if you look at any one particular person, on average, most of the friends that you have will be popular people because they're the ones you're most likely to link up with, and therefore you're more likely to have popular friends than unpopular friends. And if you do the kind of averaging, it turns out that this means that your friends, on average, have more friends than you do. So you always seem to be the odd one out. All your other friends are much more popular than you are, they've got lots more friends. And that's just a natural outworking of the way friendship networks naturally grow. This is called the friendship paradox. You can look it up on Wikipedia if you want to. But it's the sort of kind of result that you can kind of come up with when you look at social networks. This might seem sort of unimportant, but actually it's kind of useful when you're looking at controlling diseases and who you want to inoculate, or controlling crime, who you might want to put into prison. These are similar sort of things that you might want to do. So there we are. You can test this out on yourselves and decide whether your friends do actually have more friends than you do. And if they do, don't worry, it's the mathematics. Okay. So that's how friendship networks work. And here's just an example of a typical... I took this from an American website, so you can see they've got these wonderful American names. But it's such a good diagram, I thought I'd keep it in there anyway. So this isn't untypical. There's Barbie, who has lots and lots of friends, most of whom have far fewer friends than Barbie does. But this friendship network neatly groups into three. Barbie's friendship group over here, and then Diva has her friendship, I think it's a woman, her friendship group over here, and Ken has his friendship group over there. And here is a friendship network which has naturally divided itself into three communities. And if you take that large network of interactions that I showed you for a city, that naturally divides itself up into different communities. And what's a community? It's a group of friends who are all friends with each other, but don't really have many friends outside. That's a community. So there's lots and lots of network connections within it, but very few to another community. And cities form communities, and to a certain extent, it's the way they form communities and the communities that they form which then define the character of that city. So we can do some mathematics on this. The next couple of slides are going to be a bit more mathematically heavy than the ones earlier. Any network will have R essentially self-contained communities. So you can be quite precise how you define this in terms of the number of network connections within the community as opposed to the ones outside. And any network has a thing called the modularity, and that basically says if the modularity is 1, there are very, very clearly defined communities. There's very little, almost no interaction between different communities. And if it's 0, it means really everyone's friends with everyone else. There's no great separation between people. So it's not really forming communities. Everyone knows everyone else. So these are numbers, well, that you can actually compute, and we'll compute some of them in a second. So the next slide is mathematically quite heavy, just to show you how these computations work. In order to make sense of this huge, huge network, we have a thing called an adjacency matrix, Aij, which is a big matrix which has the value 1 if person I knows person j, and the value 0 if person I doesn't know person j. So it's just a very large array of 1s and 0s. Each person I will have ki number of friends, and in any network there will be a certain number m of total number of friendships. And then Newman, in a seminal article about 10 years ago, worked out how you could compute the modularity, and this was the formula he came up with. This is an important formula, and basically, although it's a lot of math and looks rather confusing, what this is saying is the city is going to form communities if within a community you have lots and lots of interactions and there's very few leakages over to other communities. I won't dwell on exactly this, but this is the formula that we use in order to work out how connected a city is. So let me show you how this is applied. So I want to take you to a very nice paper that my good friend Peter Grimrod wrote fairly recently for the Royal Society, where he did a living laboratory experiment on these cities within the UK. He did London as well, but London didn't fit on the page. It was just too complicated. We'll look at that in a minute. London, in many respects, is very different from any other city, in many respects, one of which is that I can't fit it on the page. It does have my own city of Bristol, well, the city I lived in for 30 years. What are we looking at here? What we're looking at here are the friendship networks as defined through Twitter. So on Twitter, you can kind of basically like someone, and if you like someone, that gives you a marker, and that allows you to draw one of these edges. So this is the Twitter sphere, the Twitter networks of UK cities. And that gives us actual data that we can use to say, does that city split into communities or not? So having got all this data, Grimrod and Lee then did some analysis. So they took, for example, the city of Bristol and started assuming it was one big community and then started to divide it up. And they carried dividing it up, monitoring the modularity until the modularity didn't increase anymore. And at that point, they said, right, we have identified the communities of Bristol. Oh, sorry, before I do that, let's show you to the communities of Leeds. They also looked on Twitter Spaces what people talked about, and that allowed you to group people into communities. So in Leeds, they found two distinct communities, and here they are in terms of the Twitter feeds. You might work out which group that is, as opposed to which group that is. Okay. So I think you might appreciate that this is a group that kind of likes football. So these are two distinct communities in terms of the sort of things that were being communicated on Twitter. Okay, there's a lot actually going on in these two, some of which is quite awkward. Okay. It's interesting that Yorkshire is nice and big there. So let's have a look at Bristol. So what's happening with Bristol was they started assuming that Bristol was one big lump, and then they started dividing it up and dividing it up and dividing it up and dividing it up. Ignore the dotted line. The green line shows how the modularity increased. And they came to the conclusion that the city of Bristol, where I came from, divided itself up into 74 different communities. Here are the results for all of the cities. So Edinburgh, where my daughter used to live, has relatively few communities. It's essentially quite well connected. There's Bristol with 74, and London has 156, and its modularity is very high. So that's telling us, I suppose, that London is a very, very ethnically or whatever diverse. We have lots of communities which might be due to ethnic background, wage, salary, class, age, all that sort of stuff. Is dividing itself up a great deal. Birmingham, on the other hand, is much more homogeneous. Another thing you can do, once you've worked out what the communities are, is that you can have a look at them and compare them with other cities, and you can ask the question, which city can I make out of other cities? Can I take the communities of one city and turn them into communities of another? So say Leeds has 133 communities, Bristol has 74. So basically Leeds has a wide variety of communities, but not Bristol. And that means that Bristol can be made up of bits of Leeds, but Leeds can't be made up of bits of Bristol. That's kind of an interesting conclusion. And this table here shows that communities from Bristol can make up Manchester, Nottingham, Edinburgh, and Birmingham, but not Leeds. Whereas bits of Leeds can make up everything. Okay, so it's interesting. Leeds and Manchester turn out to be cities that you can make anything out of. So if you want to do some sort of social campaign, something that works in Bristol because of its smaller community structure might work better than in Leeds, where you're trying to work with a much greater variety of people. Again, London isn't on this because it is so big and so much is going on that it kind of blows everything else away. So that's really interesting. It shows you where a formula, this formula of Newman's, applied to looking at these networks, allows us to see how the communities build themselves together and what then might work for one city in terms of future planning might not work for another. Okay, so let's move on to travel. Very important subject. So keeping cities and moving is one of the biggest challenges that road authorities face today and into the future. So in my city in Bath, they are just about to bring in this congestion charge. I know in London you've had it for a while, and we're just about to have it in Bath. And there's lots of debate about what cars should be included in the congestion charge, should they count buses, and which parts of the city it should apply to. And this is a big debate and will change the character of Bath. So cities have road networks. Some of these you can plan from scratch if you're building a new city like Milton Keynes and like roundabouts, and some you just have to take existing roads and you might want to change the priorities to change things. And one thing I'm sure you'll all appreciate is that even quite small changes to the road network, if you shut the wrong road or put traffic lights in the wrong place or have roadworks, it can lock the rest of the place solid for the rest of the day. Okay. So we have to be very, very careful. Again, how do we study this? Well, the classic way to study this is to use networks again. Networks, instead of networks between people, networks where you have junctions and the connections between those junctions. And I'm proud to say London started all this off, in a sense, in that one of the first network maps is this glorious thing, the tube map, which was first produced in this form in 1933. And what's happening in the tube map is really wonderful. You have the stations here, and the tube map shows you the only thing you really want to know, which is what station is connected to what other station. It doesn't show any other detail, like how far you are away from a station or how long it will take, because you don't need it. It shows you exactly the information that you need to plan your journey from Barbican, which is where we are, to, say, Paddington, which is where I need to go to get home. So that's a really, really useful network. It certainly wasn't London where the first network was. Arguably the first traffic network produced to understand a city was done by the great mathematician Leonhard Euler in the 1800s, looking at the town of Königsberg, which was then in Prussia. And he was looking at Königsberg has islands, and this is a network which looks at the roads which go across the bridges connecting the islands. And he produced this network to answer the question of whether you could walk around the city going over each bridge once and once only, which, in fact, you can't do. And there's a whole Gresham lecture on that just alone. But this was one of the original networks. And one of the actually wonderful things was that Euler came up with the theory of networks to solve the bridges of Königsberg problem. That theory then became hugely important in friendship networks, in Google and telecommunications and all of that, but still is very important for the original problem of dealing with traffic. Here's another network. This is inner Edinburgh, which shows you the complexity of modern cities and the sort of decisions that you have to make. What this network doesn't show is the fact that many roads in Edinburgh are one way, and also that Edinburgh is very three-dimensional, so that you can be driving on one road and you find another road which you appear to think is on the map, connects with your road, is actually going underneath your road. So really kind of complicated. Okay, so what's important about this? Well, what a town planner would typically do if they want to get the traffic flowing well in a city is to take these sort of networks, and on a computer you can kind of simulate traffic going around in different ways, and you can see what the effects are of shutting roads or producing new roads or putting traffic lights. And this is a vital way that modern cities are designed. However, one of the features of network analysis is that the conclusions behind it are often different from what our intuition would suggest. And one of the conclusions of network analysis is sometimes if you add more roads into a network, it can actually make the traffic worse. And I'm going to take you through that because it's an interesting piece of mathematics which has many other implications to city design. This was tested experimentally, not entirely intended. In New York, there's 42nd Street, which is one of the busiest streets in New York. If you ever go there, it's a huge amount of traffic. And on Earth Day in 1990, they thought for an experiment, just to make the Earth a better place and less polluted and blah, 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 they would shut 42nd Street. And they were hounds of protest. You'll shut 42nd Street, New York will lock solid. So they shut 42nd Street, and the traffic actually improved. Wow. I mean, what was going on? Well, from a mathematical point of view, this wasn't too surprising. And I'm going to take you through a little calculation to show you why that happened. It's a thing called Braess's paradox. And I'm going to try to show it through this relatively simple diagram, which I will immediately say I've essentially stolen from Wikipedia. So Braess's paradox imagines you have a start and an end, and you want to get traffic from the start to the end. And we have a road network with junctions A and B. And in one way to go around the road, you go along this dotted line, down this solid line. This solid line is a good road. It always takes 45 minutes to go down that road. And this road is a bad road, and the more traffic you've got on it, the slower the road gets because it gets congested. So the time it takes to go down this is capital T, which is the amount of traffic down the road, divided by 10. So if you get 1,000 cars going down that road, then it would take 100 minutes to go along this road. You have the same sort of road here and a good road here. And this is a shortcut which we will initially close so that the traffic can't go down this road. So if you want to get 300 cars through this network, each of these two routes is identical, so it makes no advantage for one car to go through either A or B. So 150 cars go this way, 150 go this way, and the time it takes them is 150 divided by 10, which is 15 minutes down this road, plus 45 minutes down that road, which is 60 minutes. So every car takes 60 minutes. Okay, so the town planners say 60 minutes is too long, let's open up a shortcut. So they open up a shortcut from A to B. It's a one-way street, and it takes you 20 minutes to go down it. So at the moment, it's taking cars 60 minutes, but we're going to open that shortcut. So they open the shortcut, and imagine one car notices that that shortcut's open. So 150 cars go through A, so it's taken 15 minutes. It then, just over 15 minutes, it then goes down this road here, and that takes 20 minutes, and then it takes 15.1 minutes to get through there. So that one car, by going through the shortcut, takes 50.1 minutes. It's cut 10 minutes off its journey. Fantastic. So the shortcut has cut 10 minutes off that car's journey. Unfortunately, lots and lots of other cars realize there's a shortcut, and they all follow that first car. And the system works until all the cars going through the system end up taking the same amount of time. And if you do the calculation, you find you get the same amount of time if 250 cars go to A, and then 200 go down the shortcut and along here, and 50 cars go down there and along there. And what happens then, if you work it out, is the total amount of time it takes is each of these calculations takes the same, and it takes 70 minutes. So if you open up the shortcut, all the cars think, oh, I'll go that way to make my life better. But because they're all going that way, they all end up jamming up the roads, and so everything goes slower. So opening up a shortcut jams up the network, and the whole thing slows down. So Braess's paradox tells us that we have to be very, very careful and think very mathematically about things and look at the big picture rather than just saying, if I open up a shortcut, things will be better. And we'll see this happening again later on. Okay, so that's travel. What else do we need to worry about in a city? Well, crime. So I'm going to start with a lovely story. The New York Times had heard that a crime had been committed in London. They were terrified about this for all those Americans going to London, so they asked people to report on crimes that had occurred to them when they were in London, and they got the following replies. A stranger tried to talk to me on the tube, so I reported him, because it's illegal. I ordered some tea, and they put the milk in first. It was terrible. I asked someone how they were, and they actually told me. And this is the worst of all. Someone yesterday stood on the left side of the escalator. So these are appalling crimes. It made me feel proud to be a Londoner when I read this article in the Times. But more seriously, crime is a problem when you get lots of people together. And it's a subject which mathematicians have started to study, both to analyse what's going on and see if there are ways of reducing it. And in particular, Andrea Bertozzi at UCLA has led a huge amount of very significant work studying the way crime occurs in Los Angeles and then stopping it before it starts. And her work has actually been very, very effective. It's helped a bit because Los Angeles looks like that. Okay, it's on a grid system, and the road network works like this. And Andrea and her group essentially assume that criminals go around the grid system and commit crimes every so often. And the way she models this behavior is to firstly assume that you've got criminals moving around, and secondly, that they will commit a crime at random, but they're more likely to commit a crime if there's a kind of an attractiveness to the network. So if you get several crimes occurring, you kind of get a crime hotspot, and that makes it more likely that people commit crimes in the future. There'll be increase in victimization. So mathematically, this is modeled by saying, well, assume criminals arrive randomly at a junction, rather like buses do, but there's an attractiveness, A, which is how likely the crime is to be committed, and in a short time, delta t, the probability of a crime occurring is 1 minus e to the minus a dt. So what that means is if the attractiveness is high, a is high, e to the minus a is small, and there's a high probability of committing a crime. If the attractiveness is small, there's a low probability. And the model basically works by saying, we'll assume the criminals move around. If they commit a crime, then that's it for the day, they go home. Otherwise, they carry on and they may commit more crimes. But as crimes get committed, the attractiveness of further crime increases and diffuses out, rather like if you drop ink on blotting paper, it starts to spread out. And that's kind of how attractiveness goes. And if you take this network and you take this model and you take all of this, then what you get is this. That is a model for crime in Los Angeles, where you get regions where there's low crime and these regions here where there's a lot of crime. Okay, these are called crime hotspots, and you can go out and look for them, and they absolutely exist. So there's a lot of validation of this model. The model I've described is a little bit hard to work with, so mathematicians tend to prefer to work with partial differential equations. I'll show you what these are, just so you can see what they like doing. That's the sort of model that they use, where A, here's the attractiveness. That's how it changes with time. This is diffusion. Rho, here's the density of villains. These are various constants floating around. And these are the differential equation models that Andrea's group work. I won't bother you with the details. Police. Okay, so they get very interested in all this, and they say, well, what we will now do is we'll start to target these hotspots. So they've evolved a procedure in Los Angeles for dealing with crime, which is called rather wonderfully cops on the dots. Cops on the dots, okay? And this is the model for cops on the dots. D is the number of cops. This is the deterrence. This measures how much deterrence you want to put on. Again, lots of differential equations, which if you like that sort of thing, you'll like. This is my job, solving these. We use exactly the same sort of models to look at animals and also even to look at the weather. This is then something you can model the effect of various strategies. So this is where you've got no cops. There are your dots happening. If you move the police in, at a certain level, what happens is the dots get bigger, they get lower in the amount of villainy, but they spread out. And then at a certain critical point, the dots sort of break up completely. And then if you kind of put even more police in, you get this where the crime essentially is at a much lower level across the city, so you can kind of break it all up. And it's these kind of stuff that's being used in Los Angeles to help combat the crime there. I'm not sure whether it will kind of work the same way in London, because London's a very different type of city, but it does seem to be effective, and it's a tribute to the mathematics that's used. Okay, so we talked about crime, but why do most people go to cities? Well, they obviously don't go to there to be burgled. Lots of people go to cities to shop. Here is the Westfield Centre. I'm not sure if anyone here has been there, but 50 million people go there each year. This is in the East End of London. It's the largest shopping centre in the country. The next largest is in Newcastle, Jubilee Centre up in Newcastle. And interestingly enough, study of retail mathematically is possibly the oldest bit of mathematical work that's been done to study cities. It's been going on since the end of the Second World War. So the optimal placement and growth of retail stores has been studied since the 60s. Here's a rather more elegant retail store. This is Covent Garden, just for contrast with that ghastly thing I put up earlier. And I'd like to highlight here, there's Alan Wilson and his group at UCL have pioneered this. And the first thing here is the sort of model that they use to allow stalls to work out where to, whether it's worth building a store in this particular area. What's going on in this formula? SIG, J, is the amount of wealth that's coming into a store J from people moving from Ward I in London. And this is equal to EI, which is the per capita expenditure for that ward, times the population, times the pulling power of the retail centre, e to the minus b to CIJ, where CIJ is the effort it takes you to get from Ward I to Ward J. Okay. So to get to the East End of London is a bit awkward. It's hard to get to places like the Excel Centre. And AI is a kind of number that you use to calibrate the system. Wilson and his group have built up this model for all the wards and all the shopping centres and tested it very carefully, and there's a lot of evidence that this does actually work. It allows a shopping centre to work out whether it's worth building a store in a particular area or not, and well tested and widely used by retailers. This is what we call a static system. So essentially describes where things are now and what happens if you put in a single store. They have a more complicated model here. This one here tells us how the growth of a particular centre, how a particular centre will grow. And basically, centres grow if their revenue here is bigger than the cost of running it. But the revenue depends on all the other stores as well. So the revenue that one store will get will depend a lot on whether there are other stores nearby sucking revenue out from it. And these are, the sort of models that retail centres use to see how well they will grow and indeed compete. These equations here are called Lotka-Volterra equations, and they are the same equations that are used by biologists to study animal species competing against each other. So shops competing against each other and rabbits and foxes competing against each other basically obey the same mathematics. So here are two scenarios that you can get. Here is one where a superstore in pink, which is labelled here as predator, because this is a Lotka-Volterra, grows and grows and grows and completely wipes out the opposition, which occurs in some places. And another one is where you get cycles where one store beats the other one, and then this one revives, and that beats that one, and you get these cycles going round. So at the moment, we have Morrison and Tesco's and Sainsbury's all competing against each other and going up and down. And again, these are sort of things that can be analysed and predicted. Okay, so the last thing I want to talk about before I get on to London is just to say where are future cities going. And the real buzzword that's around at the moment is this: it's the smart city. And the smart city is certainly what we're getting in Bristol now. I'm not so sure how much of it's happening in London, but in a smart city, you have lots and lots of sensors everywhere. And these are sensors that can either be on lampposts, so they're static sensors, or there might be sensors that you are carrying around on your person, either because you know you are, like you've got something on your wrist, which is sending information to your health centre, or your mobile phone is simply giving data away. And in a smart city, all this data is collected, and then it's fed into some humongous place to monitor and manage all this sort of stuff here. So by sort of knowing where people are moving around, you can actually use that to manage retail and government and stuff like this. And this is where things are heading, use of a large amount of sensor data. All this leads to more efficient use of resources. A good example of that is currently traffic lights are controlled by local things which try to minimize the queue length actually at the light. But in a smart city, you get data from all the traffic lights, and you can optimize that to get your flow going generally. I put this up because smart cities are the city of the future. That's what's going to happen to us. More sensory information is going to take to try things more efficient. But point of caution, firstly, Braess's paradox, where we make decisions, might mean that if you take too much information, you might actually make things worse. And something which I worry about is that if it makes the city more efficient, it also means it easier to hack into if you're a criminal, and therefore we need to worry to make these things more efficient, more criminal-proof. Okay, that's all a bit serious. I thought I'd just finish this talk with something a bit more light-hearted, which is to say, as you go out through the doors, things to go and see in London which are mathematical. And there's lots of them out there. This website, which is on the transcript, is something which Marcus de Sotoy, the Professor of Public Understanding of Science in Oxford, put together to mathematically guide you around London. This is the British Museum. It has lots of great mathematics in it. This is the Rhind Papyrus, which is one of the earliest pieces of mathematical literature, and you can go and see that. St Paul's Cathedral, just down the road from here. The dome itself is a great bit of mathematics. The whispering gallery within it, if you speak there and the fact you can be heard the other side, is also wonderful. And if you do go to St Paul's Cathedral, rejoice in the fact that Christopher Wren, who designed it, was a Gresham professor. Good stuff. If you go on the London Underground, on the walls, you'll see labyrinths. Very proud of this. I was part of the team that put them up to celebrate the 150th anniversary of the Underground in 2013. And you can see these and try and work out how to get around them. And if you want to be slightly more cultured, if you go to the Tate Gallery, there's a Jackson Pollock in the Tate Gallery. What's that got to do with maths? Everything. The structures, the fractal structure is just gorgeous. I'll be returning to this in a Gresham lecture next year when I talk about maths and art. And if you really want to kind of debase yourself and do something terribly awful, but very much related to what we're doing, you can go on a smelling tour of London, and there's a smellscape of London with the various types of smell carefully calculated using sensor information. And with that, thank you very much. So hopefully time for a few questions. A couple of questions, so I went over a bit. There's a lady there.
Just a couple of things. Does the technology and all the social networking affect the maths at all in terms of, all the networks that you drew up? It's made it more extensive, more something.
Yeah.
And also, does that change based on the culture? I mean, Chinese cities would be very...
Yes, so Chinese cities do have a very different structure from UK. It's much harder for us to get information on those, of course. But the basic maths is the same all over the places, yeah. Another question there.
About maths and pedestrianisation.
Yes.
You didn't. It seems to me amenity is very much improved by pedestrianisation.
Yes.
And well, I presume you could perhaps calculate the effect of pedestrianising.
Yes. So
Regent Street and Oxford Street.
I should have said I didn't cover this today because I did this last year in the lecture, Can You Do Maths in a Crowd? So you can study the way people behave in crowds. And that's a marvellous application of maths to see how cities work. And we have, the reason I was in Tokyo was to work on the crowds in Tokyo and work out the best way of directing them around and getting them across junctions. So if anyone wants to hear about or read about the way maths is used to improve the dynamics of crowds, have a look at my Gresham lecture, Can You Do Maths in a Crowd, which I delivered last year. Well, Braess's paradox indicates that you may actually make things better. I think we have to stop there because I think we're about to be turfed out. Thank you all for coming. Next month, which will be during Science Week, I'll be giving a talk about mathematics education, that very controversial subject.